Good morning, ladies and gentlemen. Today we're going to look at the very start of quadratics, which is basic factorising. A lot of quadratics is algebraic manipulation, and then from there we can go on to solving more complex equations. So, starting off with 2 or 3 very simple techniques that you should know from year 9 but are worth just jogging your memory about. Firstly, and quite often we get so involved in sort of complex factorising that we forget that sometimes it's easy. Sometimes removing a common factor is the best thing we can do. Has to be the highest common factor. So note here the highest common factor is 3x. If you want to, you can think about this as 3x multiplied by x minus 3x multiplied by 7. Now what comes out is the 3x, and we bring it out the front. 3x, then what's left on the inside is x take 7. Now note, no matter what type of factorising you do, you should be able to check by expanding it out should get you back to the original. So if we expanded this out, 3x times x is 3x squared, 3x times negative 7 is negative 21x. And we're back to the start. So it's worth just doing this check there. Alright, other simple factorising techniques? Difference of perfect squares. Now from year 9, you'll know that difference of perfect squares starts off looking like this, and that simply factorises out to a plus b, a take b. And we can check by doing this. So FOIL, firsts, a times a is a squared, outers minus ab, inners plus ab, lasts minus b squared. These two terms are like and they cancel, leaving us with a squared take b squared. So we can factorise a take b squared, a squared take b squared with a plus b, a take b. Now you've seen that before, but it pops up again and again in disguises. So sometimes you're looking for a nice squared number, and you get something like this where there's no obvious squared number. So what we have to do first is take out a common factor. 3 bracket x squared take 9. Now you're thinking, actually, this is getting closer to what I was after. 3 bracket x squared, well, I could think of that as 3 squared. 3 bracket x plus 3, x take 3. And that there is fully factorised. Note, the dead giveaway, a common factor with all of these is they all have a subtraction between two terms. Look for the subtraction as a sort of hint that it might be DOPS. Alright, how else could DOPS appear? Could appear like this here on the bottom left. This 16 we can think of as 4 squared. So our a in this case is x plus 2, and our b is 4. We can think of that as a squared take b squared. So when we factorise it out, it becomes a plus b, except we know that b is 4, bracket a take b, which becomes x plus 6, x take 2. Now if you expanded and simplified this, and then expanded and simplified this, you'd end up back at the same point. Right? Now, once again, we were very lucky, or good to notice that that could be written as 4 squared, and this was something squared as well. Sometimes, however, there's nothing obvious to be squared. I mean, what's 7? What squared gets you to 7? Now, interestingly, there is a number squared that gets you to 7. We don't know what it is exactly. We have a decimal approximate, but we just call it root 7. Root 7 squared gets you to 7. So this can be factorised as x plus root 7, x take root 7. And we can double check if we want. We can double check. So x times x is x squared. X times negative root 7 is negative x root 7. X times root 7 is plus x root 7. Then root 7 times negative root 7 is just negative 7. The two terms in the middle, once again, are like, and they cancel. So x squared takes 7. So even though there's not a squared term there, as in 7's not a special squared number, we can still do it. Alright. Second technique, factorising by grouping. This works when there are several different variables involved, and also forms the key of factorizing by grouping when we're using trinomials, or splitting the x term in a future video. Don't stress. Alright, here we sort of notice that actually this half can be factorized by taking out a common factor, and this half has a common factor. So what we do is we remove the common factor from the left-hand half, which is x, leaving us with x take a, and we move the highest common factor on this half as well, which is going to be the minus 4 here. And the reason I'm taking out minus 4 is because if I remove the minus 4, these now are the same. And if we're factorizing by grouping, we should be aiming for them to be the same. Now, this is a conceptual leap for some people. So if I just imagine this whole thing as, well, b and b, this would look like xb minus 4b. And you would factorize that by chucking the b out the front. b x take 4. And that's effectively what we're doing here. So we wouldn't normally put it in terms of b, but we can take out the common factor. The common factor is x take a. And what we're left with is x take 4. So in order to factorize this here, we would go like that. I'll show you again with another example. So, left-hand half, we would be looking to take out 3x, and what would be left would be x take 2a. Right-hand half, we're going to take out a negative 7, and what will be left with is x take 2a. Then the x take 2a is the same, and this only works if they are the same. So we take that out. X take 2a. And what's left is 3x take 7. Note that factorizing is taking something that has multiple different terms, 1, 2, 3, 4, and writing it so that there's two terms multiplied together to form the original. 2 multiplied together to form the original. And that was true with whatever we've done so far. Here, perfect squares, two different terms. I hope you can see my cursor. We write it like this, so there are two terms multiplied together to form the original. Two separate terms, separated by plus and minus, multiplied together to form the original. Basically, we're trying to eliminate the pluses and minuses that are separating them. Alright, perfect squares expansion. This we covered in class, but it's worth having on video because I see this about 10 times a year, 10 to 100 times a year, and I die a little inside. People think that this equals that, and it does not. Two ways to think about it. One way, a plus b all squared is really a plus b multiplied by a plus b, which is equal to, if you do FOIL, a squared plus ab plus ab plus b squared, which is equal to a squared plus 2ab plus b squared. We'll use this later with completing the square. The other way to think about it is slightly more, I guess, diagrammatic. Is a and a b, a and a b. This is a times b multiplied by a times a plus b. A plus b multiplied by a plus b. A and a is a squared. A and b is a plus ab, b squared. It all adds up if you sum all of those to be the same here. Alright, I've zoomed through that quite quickly, but hopefully you've seen several different methods of factorizing. Thank you very much.